So thanks for the opportunity to speak. I thought a lot of, in fact, some of the drivers that you just heard are similar to the ones that we have, with a bit of a unique flavour and certainly a different solution at this point in time. And some of you have heard this presentation, so apologies, although I've got a little bit of new material in there for you. Does that? No? Oh, that big green one, there we go. So Chris, let me take an aside just for a moment. Chris in his introduction said, I've done some other things. So if you missed purely academic at eResearch last year, I'm sorry. But it'll come to somewhere near you soon, perhaps. We just did a reading in San Diego. And it's a comment on academia, which perhaps is a background for some of my comments earlier this morning on what it's like to think that we're at the bleeding edge. So that was certainly a lot of fun. But what you may not know is that in addition to computing, I also make stained glass windows. So there's some of those, and so the good thing about that is they have nothing to do with computing at all. But a couple of months ago I was in Barcelona and I discovered that actually they do. So the Barcelona Supercomputing Centre has what's been voted as the most beautiful machine room in the world, because that's their Mare Nostrum machine down there, and it's actually in an old converted chapel with stained glass windows. So I'm just waiting for an opportunity to pull all of this together. We'll see how that comes. All right, so something a little bit drier perhaps. Let me just say a thing or two, although of course when you look at the LHC you don't need much more introduction as to what's happening in the drivers for this, but what we're all about doing is bringing data together with the computation. So data-intensive computing is about all of those words in that sentence, and often when people talk about data and certainly a lot of the national dialogue, it's about the data, and they forget that you actually need to either compute over it or it's coming from computations. And so this can go either way. So we can either take enormous amounts of data from instruments like the LHC and compute over it, and that's a particular class of problem, or we have computations that themselves generate, and in fact are instruments in a sense, digital instruments, that generate enormous amounts of data. And so we want to support all of those. And so a lot of the focus of our work has been, how do I make that happen? And let me just say as a side comment, we've had a debate over many years about do you take the computation of the data or the data to the computation, but I think it's the high-speed networks that AARNet is putting in there that actually skew that. And as you all know, you can move an awful lot of data if you actually make effective use of the network. And that mitigates a little bit of this question about which one do I move around where, and you'll see that come out in our architecture. So whether it's a climate model that is leveraging an enormous number of floating point units on a big scalable parallel machine and generating data that is then analysed perhaps by some deep learning network or visualised, or where it's the other way around, really doesn't matter that much. What you do need to do is put in infrastructure that supports it, and again, looking at the two ends of this, we want computation that supports large amounts of internal working memory. These computations are all parallel because they're all huge, and there's a memory pyramid in there that I'll come to in just a moment that you want to smooth out as much as possible. On the storage side, of course, you want to do long-term storage of this, so there's not much point running the experiment and then throwing the data away, although sometimes we have to do that because there's just so much being gathered. So we want significant long-term storage, and again, there's a memory pyramid in there that we'd like to smooth out as much as possible. This last point, though, about the multiple views of data is something that I feel particularly strongly about, because we've been building out storage systems that are siloed and special purpose. So people talk about object store, they talk about local file systems, they talk about parallel file systems, they talk about sync and share, and in too many cases these are actually completely separate storage systems. What we've managed to do in Medici is actually pull all of these together and treat those as views of the data. That's how I want to manipulate and see my data, but underlying it there is the one truth or the one root source of that information. So I'll come back to that repeatedly through this. So in fact there's a memory pyramid in there, and it extends all the way up to deep into the processor, all the way down to the long-term hierarchical storage. This is the way we would like to see our data, and as I'll show you in a moment, we'd like to see that move up and down that pyramid as much as possible. So there's another version of this talk that I give, which is it's caches all the way down. The underlying paradigm is that you'd like to cache the data in high-speed storage close to where you want it, but you're prepared to tolerate the fact that it will be in slower storage, which is much larger. This is the history of computing. I've been working in it now for sufficient years to see that that's always been true, and it's not going to change. The stuff that you've got inside the registers of a machine is small and fast, and the stuff where you put it is possibly tape or very high latency, slow devices out the back end, but very large capacity. So it's always been caches all the way down. What we've tried to do over the years from a computing perspective is smooth that out as much as possible. And so on the right-hand side here, we're showing software systems that have been put in place that try and smooth that out so that perhaps the programmers or the users aren't quite aware of what's really going on underneath. So at the top few layers inside the processor, it's perfectly acceptable to let the compiler allocate your registers these days. There are sufficiently good graph coloring algorithms in there that none of us allocate registers. I like to ask, how many people in the room last week allocated a register in a piece of software? How many of you copied a file from one file system to another one? Come on, own up, right? We all do that. Why is that? We're still manually moving data around the bottom part of that hierarchy because we actually don't have good enough software systems in place in general to move up and down the hierarchy. And by the way, I did ask that question once at a conference, and one guy stuck up his hand, but he was in the compilers group, so he's probably a special case. So whether you have hierarchical file systems on the right-hand side and programming paradigms that try and move the data up and down there as automatically as we can possibly do. So we've developed a bit of a reference architecture for this, in which the left-hand side, I'm sorry for the change in colour there, at the last minute I reformatted my slides and all of the background colours have changed, so what was something else has gone purple on me, so just bear with that. On the left-hand side you have compute clusters. Remember I said we need parallel machines for doing the computation. We have compute clusters and processors on the left-hand side with fairly automatic movement of data up and down at least part of that hierarchy. On the right-hand side we've got slower, higher latency but very large storage systems like tape and like made disk and the like. And I don't want to get into a religious argument about whether tape is here for the short term or the long term. We can do that over beer maybe. It's an interesting debate. But there will always be something larger and slower on the right-hand end. And then we try and move data up and down there. So that's our reference architecture, moving all the way from storage of the long-term data sets deep into the parallel processor. Now the only bit of this I'm going to talk about today is Medici. But there's the bigger talk actually says, well, what do you do inside the processor and how does that look? And actually at this point I want to credit Pete Elford, who's not here, for the name Medici. That was his inspiration and contribution to the project at the highest possible level. Prior to that it was called Mad Men, so I think he probably got a better title there. As you'll see in a moment, it actually plays out quite nicely for us. So the caches continue down through that automatically. Now here's the inconvenient truth of places like UQ and in fact many other universities, is that we are physically distributed. On campus we have an enormous growing array of instruments, plus some of our computation, plus some of our storage, and then off campus we have the long-term home of a lot of the data sets, a number of our compute clusters, and the cloud system. And that's a commercial quality data center. I can't get in there, so that's probably a good thing. But it's commercial quality data center, and we pay for hosting off campus with reasonable amounts of bandwidth between that and the main campus. But we will never put all of our instruments actually in the data center. So they will always be on campus, and there'll always be some local compute on campus. So the question is how you bridge that so that people don't spend their time copying files from something off campus to something on campus, and vice versa. So the paradigm is sort of data, everywhere, anytime across that network, which is a little bit of market speak in a sense. But we have a number of different views of the data, and they don't dictate how the data is stored and where it's stored. So at the bottom, the long-term home for this data is actually in the commercial data center on a hierarchical file store. It's presented to users through various stacks. So there are a raft of different repository systems on the left with managed data, where we present it up to different instruments. You know what, from a computer science perspective, there's not really any excuse for multiple repository stacks, but the reality is the community's sort of adopted different things. So whether it's Amero or Mitatis or whatever else, those communities have adopted them, but they sit on top of file systems. There's unmanaged data that you want to present to users either as direct mounts or through sync and share. There are clinical data sets which again managed through stacks, and then cloud access where I might want to say to someone on the other side of the world, here is a data set, you can pull that using HTTP. So that's the overriding paradigm. Medici centralizes research data storage and computation, but distributes the data on a demand basis. When you need that data set, it's moved to where you are, and it stays there as long as it's needed. I do want to highlight the fact that the cache sizes, and I'll show you these in a moment, that we're putting in place are actually as large as what would have been standalone file systems. So where people are going and buying petabyte file systems previously as standalone file systems, we buy a petabyte file system, but as a cache, and it's a cache view. So the working set of that is quite large. I can afford to hold an awful lot of data close to where I think it's been used, but not lock it there. Medici moves this around automatically between them. Our current implementation is based on a couple of commercial products. It doesn't have to be. It's just that we managed to find some software that did most of what we wanted. So there's the landscape. The landscape now is that at UQ, I have a number of caches. We have caches close to some of the instruments, some of the computers, and a hierarchical structure all the way out to the data center. There are caches in the data center as well, and that's presented to the machines that are out there. So no system has anything other than the same view of this hierarchical storage. They certainly don't think about them having the only copy and it has to be moved around manually. Now, you can actually extend this paradigm so that the storage that comes off campus, most of we're investing a lot of effort is in the long-term storage in the data center, but it turns out you can also back-end that into something like Amazon or one of the other cloud services. So the long-term home for data can be chosen on a price and policy basis, but still presented back to the campus in exactly the same way. So users operate on files regardless of where their long-term home actually is. And so we have some of our stuff going out to Amazon. We have some stuff staying on campus in the local data center for various legal, political reasons. Again, for discussion over beer, I can talk about whether I think that's going the right direction or not, but the lawyers have a view on where data might sit. And then we have some legacy data that's sitting in this case, in an Oracle hierarchical file store, which can again be presented back into the network in exactly the same way, so people don't necessarily see where it's come from, and that's very attractive. Now, this is an AARNet conference, of course. You want to see a wiring diagram, so it looks a little bit like this. And then, again, credit to Pete for coming up with the idea of calling us Medici, because now you've got names for all of these caches that can be the members of the House of Medici, who are a bunch of crooks and robbers and not necessarily very nice people. So in the left-hand top corner there is the Polaris data center, where you see a couple of caches. Capella and Giovanni are the two main caches there. One of those serves our clusters. Another one serves the cloud and is also the bridge out to the outside world. There's a what was Silicon Graphics but now HPE DMF fabric that has some local caching and then all the way up to Oracle tape. And that's presented, now you see the little lines coming out of Giovanni, that's presented with different protocols. So regardless of how you want to see the data is stored, in this case, in a DMF hierarchical file system. But it's presented to the world in different ways. So I could present it through any number of protocols. If I want a direct mount on my desktop, it might be CIFS. If I want a sync and share service, it might be a Nextcloud service. If I want it on the other side of the world, it might be an S3 HTTP interface, or if it's something like a direct mount into a cluster, it might be NSD, which is the native parallel file system of IBM. Those protocols don't dictate how the data is stored, they dictate how it's exposed to the world. On the right-hand side, you see some of the caches that are distributed around the campus. So Queensland Brain Institute, Institute for Molecular Biosciences, a number of devices in ITS, and then one in our Research Computing Centre. And on the bottom left corner, you see some of the experiments we've been running. So last year we ran an experiment, and I'll talk about in a moment, of shipping this across the Pacific over to San Diego, to Cal IT2, to see what would happen if this was distributed across the globe. So just to reiterate that point, Medici unifies data access by exposing it through different protocols. The same file. So I'm a grad student, I can have my laptop, I can sync and share. That gets dropped into a file system and then can appear underneath a high-performance computing cluster without me actually saying, copy it from the sync and share service to the parallel file system that's feeding the parallel machine. That is really attractive, at least in my world. File shares directly onto desktops, object store exposed to the world, all of the same bytes. So this started out with the need for a parallel file system. People don't talk about that too much in this world, but if you're working in supercomputing, you know you need a file system that can deliver sustained performance to all of the nodes of the machine. Remember, we're doing high-intensive data computation. So GPFS happens to expose a parallel file system into the cluster. Out the back of that, because and previously that was a, let's see if I take that out again, that is what I would have built as a standalone parallel file system into that machine. I extend this back out now and it's a cache. It's no longer a standalone file system, and it's a cache onto the hierarchical file store. Brett, I'm completely not watching the time, so you're looking at me because I'm running out of time, or because that's all right? So look at me, glare at me if I go too long. So that's now holding, and that particular device happens to be about half a petabyte. So, you know, it would have been a standalone parallel file system. It is now just a cache. And so what it sees out the right-hand side is the global namespace of the file system. Data collections are pulled into that on an as-needs basis. Now you can stretch that, and in fact we stretch that over the metropolitan area. That's what the M in Medici stands for. And so our long-term data collections can be in one place, but still getting pulled in to machine rooms around the campus. And in fact, I can run the native spectrum scale protocol in SD across that and get parallel streams without anyone thinking about it. Now you all know that there are only sort of that many protocols that will move at line speed, and they're usually embodied in special purpose tools like Grid FTP or the like. This is just hidden under the covers. So when I open a file on a machine or touch that file, it will appear in my file system at the line speed between them. And that's the beauty of this. No one sees that except the network engineers. I get calls from ITS saying, "What are you doing to our network?" Pete's in the room. Well, we just opened a file. But no one actually had to run any special tools for that. So here's a trace of what happens. This is on limited by 10 gig NICs. You can see that we can run up to that line speed. We will always push it to the limit. I won't say a lot about this, but object store has become a bit of a religious debate. In my books, object store is about two things. It's about a namespace, and it's about a protocol for getting things. And the protocol is our internet protocols. So it's about getting things through web servers, through HTTP, with a namespace that sort of looks like a URL. That shouldn't mean that I put that data in a separate standalone S3 file system. It just means that the files that I've got in my repository I would like to expose to some subset of the users as objects. But I tell you what, objects mechanisms are not the way to do high-speed parallel access into a high-performance compute cluster. And so I get the best of both worlds. If you want to pull this file to the other side of the world, this is exposed through, it's actually the Swift layer sitting on top of GPFS. So that's unified. Now there's a lot more I could say about this, but I won't in the interest of time, but here's a few bullet points around this. So we find that what we get is a more declarative machine room. And what I mean by that is it's policy driven where things are. It's not based on someone saying, I want my file in this file system. When you go out to users and you say, can we put it on tape or spinning disk, what are they going to say? Has to be on spinning disk. I'll swear on a stack of Bibles, this petabyte data collection has to be online all the time because someone might want to use it. Well, we did an audit of our file system. Something like 3/4 of it hadn't been touched in a year. So why don't we let the software decide where that's going to go? If you're really that important, I can write a policy that says Brett Rosellan's files will always stay in spinning disk. And that's a policy. And then when he's no longer my best friend, I'll rewrite that policy and his files will migrate out. But once you've locked something into one particular partition of a file system, it's very hard to move them. People know where they are, they get upset, they've got scripts that break. So my global namespace changes that. We can leverage cloud storage. If the right place to store this data is in a commercial provider on the end of a cloud file system, we'll put it there. Put your credit card in and put it there. But again, that's invisible to the people back on campus, and so that if I do want to migrate it, in fact we're doing this now, if I want to migrate it, they don't necessarily see that, other than it's now somewhere else. I can do this on a very wide area because the protocols scale. I can support repository stacks on top of it, and I can do a lot of clever things with workflows that sit above this. Okay, so Medici went east. I think it's about 2 years ago now. We did an experiment with UC San Diego and AIST in Japan, where we brought up a parallel file system in Cal IT2 on San Diego campus. We brought up a smaller system at AIST in Japan, and the trace on the bottom right is the traffic across the AARNet connection. And the blue blip in the middle there, I haven't got a pointer, but the blue blip there is when we actually move some files around. No one was aware of it other than the network engineers who said, oh, isn't that interesting? You just... so I'm hoping we'll do another experiment this year. Where's Chris? So another experiment this year where we can test out the 100 gig, see if we can do that. So we're actually talking about doing that to the show floor of supercomputing. So that was kind of interesting. And by the way, it's non-trivial. Never mind the network. You think the network's the problem. Try getting a file system to deliver at 100 gigabits. It's quite a lot of extra work. We're doing an experiment at the moment so we have lots of users of NCI who say, I have to copy all my files down to NCI before I do the work. That turns out that is an impediment for them even bothering to do it. So what if their collection appeared down on region automatically? So we're doing some work with the guys at NCI and with Pawsey to spin up some GPFS file systems there, sitting on top of AARNetX. I hope the network engineers will see this blip on AARNetX as well, because there's really no reason if we get the endpoints right that we can't go up to line speeds there. And I'll reiterate, you can move a lot of data at 100 gigabits. Or 12.5 gigabytes per second if you want to do it in bytes. And so that's an experiment at the moment that I think will make it easier for people to see their collections on region. The one thing we know is that NCI don't actually want to keep that data long term. They're not keen to become the data sink for everybody. And so if we can say it lives in Brisbane, but you're using it at this point in time, and their cache is probably going to be 0.5 to 1 petabyte, so it'll be pretty big. But if it can migrate or go cold and disappear over time, then that's also a good outcome. This is also quite an exciting experiment. We're doing some work with Amazon Web Services to say, well, how can I make the data appear in Amazon? And so what we're doing is you bring up a cluster inside AWS. That's just a virtualized cluster. You build up a spectrum scale or GPFS cluster next to it. And that again behaves as a cache. So I go and get blocks from Block Store. I spin up a GPFS cluster on the top of that for as long as I want that whole cluster to exist. I put my credit card in, I bring up a number of machines, I do the work, and the data collection gets pulled from Polaris into the cloud. It stays there for as long as and new files that are created will appear there, and then they'll migrate back out to the data center if they've been modified. So that's work in progress as well, and we're also trying that with one of the other commercial clouds to see what that looks like. So, in conclusion, apart from anything else, it's a great name for a project because it's spun out a whole stack of mugs and t-shirts and tea towels. If you came to eResearch last year and didn't get a tea towel, then you should come along this year. We'll have some more. I'm thinking of doing a new one. Had a big argument with my marketing person, but it is the data fabric of choice. So that's what you. Yeah, she didn't get the joke, but anyway, I guess it's a dad joke. But they're great tea towels, so if you've got them, they're really good, quite good for drying dishes. So we have leveraged some commercial files, commercial products in this space. That's also something worth talking about. It's got its advantages and disadvantages, but you know, I'm not fundamentally opposed to commercial products if they do what you actually want. Sometimes people forget that. And the experiments that we're doing at the moment, which is the new stuff, I suppose, for those who've heard most of this talk before, we're taking it up to James Cook University as Medici goes north. We will continue the US experiments, and like I said, I'm hoping we'll have an endpoint into the show floor at supercomputing in Dallas this year, in November. We'll take it west to Pawsey, south to NCI, and to the Amazon as well. So on that note, I will finish.